Hello, thank you all. Thanks, Bob Madam, and for giving me an opportunity, and thanks, sir, for chairing this session, and thanks to all the people who are attending. Okay, so we're going to learn quantum algorithms. So this is the agenda. We'll try to get some introduction and then see how these algorithms got evolved over a period of time, and then finally we will be going a little bit detail. We will see these algorithms in detail. Okay, I would say these are not algorithms; they are like magic tricks. Okay, so later you will see why I call this as source magic or Grover's magic or DJ magic. Okay, so what's a quantum algorithm? It's a step-by-step procedure. Okay, like what you see it in classical algorithm. Only thing it runs on a quantum computer to solve a computation problem. So that is also like a classical thing. Only the different major difference is it uses the principles of quantum mechanics such as superposition, entanglement, and interference. Okay, so superposition gives the parallel exploration of many possibilities, the parallel computing power. Entanglement gives correlation between different qubit states, which will be useful in um, quantum neural network, and it's also used in at some places, but superposition, in my view, it's very important, and entanglement is also used in teleportation like that. Interference will happen actually without your knowledge. It happens. Okay, so we will try to identify where this interference is coming and helping us. It cancels wrong answers and amplifies the correct ones. So why do we need quantum algorithms? I think you know the answer, because solving certain problems in classical way is too hard or too slow. Okay, examples we can consider factoring large numbers or simulating molecules, simulating the nature. So it takes plenty of time. Okay, so that's why we are going to use quantum algorithms. Unlike classical computers, where the performance is often tied to the processor speed, number of cores in a processor, or number of processor itself, right? You have more GPUs, more cores in a CPU, like that. But in quantum computing, it's the clever design of quantum algorithm that unlocks the true power of quantum computing. So all that designed with this set of quantum mechanical principles. Okay, they are foundational to quantum computers future impact in cryptography, chemistry. There are many more applications. I think tomorrow you will see, tomorrow or day after you will see the applications. You will see many applications of quantum algorithm. So little bit going back in the history, you know that the concept of quantum computing was really suggested by Richard Feynman. Uh, he said you cannot simulate nature with classical computer. It should be quantum way. And then, of course, he made, I think, in '69 or somewhere. Afterwards, nothing much was happening as quantum computer. And then Deutsch was the first person who said it can be you can build a quantum computer and that can solve problems faster than classical computer. Okay, so they did in '85. He's a British physicist. Later, his theorem or his algorithm was modified so that you can find out a function is constant or a balanced at faster than classical computer. Then you are familiar, I think everybody talks about source algorithm, which factors large intelligence efficiently. Grover's algorithm, it can do search better than classical way on an unsorted database. Okay. Parallelly, you have other mathematical simulation-oriented algorithms like QFT algorithm, quantum Fourier transform. You know what is Fourier transform in classical computer, right? If you have worked on signal processing, you know from time domain data to frequency domain data. Or if you even if you have worked in image processing, you would have used discrete Fourier transform. So similarly, we have Fourier transform, which is being used by source in this algorithm. There are walk algorithms, not many people use, but this I like this algorithm, HHL algorithm, because it is used in many engineering applications, solving systems of linear equation. You know, simultaneous equations. It comes in many places in modeling and simulation and things like that. CFD, FEM, and all. So this is very useful. Of late, we are seeing a hybrid and variational algorithms. So what is hybrid? You combine classical computer along with do certain operations in classical computer and certain operations in quantum computer. It's because today our quantum computers do not have sufficient qubits, and there are issues like noise, drifting, decoherence, and all, right? So something where classical computers are good, we try to make use of it. Variational algorithm is something like you remind the structure, the width of the circuit and depth of the circuit is same, but only the parameter inside the gate. For example, if you are using a rotational gate or X gate, so the angle you vary it, okay, and then try to get the required answer. So how do you vary, on what basis? So that you may do it in a classical computer by in an optimization technique and all, and then bring that value. You run the same circuit with different parameters. So that's called variational algorithms. Some of the examples are given here. Variational quantum eigensolver. It's used for modeling on the molecules. QAOA. Okay, so that helps to solve combinatorial optimization. Example, max-cut problem, you may be familiar. And then quantum machine learning algorithms are there for both support vector machine, neural networks, and all. Okay. And then nowadays people use, even finance guys use quantum computing, particularly quantum amplitude estimation algorithm. It works like Monte Carlo simulation for them, but much more efficient way. So if you want to know more about these algorithms, actually I have videos. I think for on each of these topics you can have it. But today we are going to deep dive in these three tricks, right? So before I move on to the tricks, there is another trick by nature. It's happening in quantum computer, which you don't see it in classical computer. It's called phase kickback. So ideally, it should have been covered in circuit because for want of time, maybe we didn't touch it up or we didn't cover that. So what it does, what is phase kickback? So you know this gate, right? Control not gate. So this is control gate, this is target gate. So typically the state of this target qubit will change based on the state of control bit. That's a normal thing. But under certain conditions, the target, the phase of this will be kicked back to control. Okay. So, and that is very useful thing in many applications. Later you will see. Okay, let's try to understand this circuit. So we'll start with 0. When you apply H, it will become plus state. So you start with 0, you apply X, it will become 1, and this will become minus state. Now, let's try to put the mathematics behind that. So we are going to combine into a single matrix, that is two tensor H matrix and control. And you know that I think whenever you have two qubits, your combined matrix will be 2 square by 2 square. Similarly, if you have 3 qubits, it will become 2 cube into 2 cube. So, right. So what you see here is 4 by 4 matrix representing H control knot. So you can do that multiplication. Only thing, cron or I mean, you have to do tensor multiplication, because this is 2 by 2, this is 2 by 2. When you do tensor multiplication, then only it will become 4 by 4. And then this by default it is 4 by 4, right? So this will give you this matrix. So whatever I circled here, it will give. And where it is going to operate, it is going to operate on 2 qubits which are in 0 and 1 state, right? 0 and 1 state. So 0 and 1 state. So this is nothing but 0 and 1 state. I do not know whether you are aware, for multi-qubit system. For example, in a 2-qubit system, we will have amplitudes of 0, 0, 0, 1, 1, 0, 1, 1 here. All right. So when I say 0, 1, it's all other amplitudes are 0. But when I do this operation, all superposition states will get this one. I mean, get some amplitude. Only thing, the phases of 0, 1 and 1, 0 are negative. So I can write this in this form, and then later I can do a kind of factoring, right? Representing in tensor product of two states. So that is what is done here. And this you are familiar, right? This is nothing but minus, and this also minus state. So originally it was in plus state. By applying C naught gate under certain conditions, this has become minus minus. So that is what is given here. So under certain conditions, C naught gate, when you apply, so the phase will be kicked back. When it's plus, nothing happens. The phase is kicked back. So minus is, it's already in minus, so it will become plus. So this is very, very important thing, right? So what is this? So the black sphere represents minus minus state here. So let's jump onto Deutsch-Jozsa algorithm. So what problem it's going to solve? The problem it's going to solve is, there is a Boolean function f which takes input a string of bits. Okay, suppose I have a Boolean function. So you can give any input. Okay, maybe it depends on the size of your problem. Suppose your problem size is 4, 0, 1, 1, or 1, 0, 0, or all ones. Like that, there will be 16 possibilities, right? So you give any, when you give all the inputs one by one, for every input it will give either 0 or 1, not both. Okay, either, it depends. So what it depends? It depends on the property. So mathematically you can represent that it takes a string of bits, but and give us one bit. The bit can be either 0 or 1. Simple. So now it has got a special property that this function is guaranteed to be either constant or balanced. So what is constant? A constant function returns all zeros for all or all ones, meaning, so this will, if it is a constant, it will give either for every input what you give, it will give 0, 0, 0, or 1, 1, 1. But if it is balanced, for 50%, for example, if you have 16 inputs, for 8 inputs, it will give 0, 0. And for the remaining 8 inputs, it will give 1, 1. Balanced, right? The first is constant. All zeros are all 1. Okay. Now, I have a question for you. Suppose we have the function here. I wanted to find out what is this. So I have to make a query, or I have to give the input. So how many times I should give to know that I'm 100% confident that this function is constant or balanced? I want at least a couple of you to unmute and tell me how many times you have to make the query. That is the problem. We need to find out whether the function is constant or balanced. So in classical way, how many times you have to do? And you will see the quantum advantage later. So, okay, I will give you the answer. So if you are very lucky, 2 queries are sufficient, right? So first input, it may give 0, second input is 1, or vice versa. You know that it is a balanced function. It cannot be anything else, right? It cannot be anything other than constant or balanced. But if your luck is very bad, what happens? Suppose 16 inputs are there. You give 8 inputs. You got all zeros. Can I say confidently it is constant? No, right? For the ninth input, it may ninth input onwards, it may give all ones. First it eight input, it can give zeros afterwards. So what you need is half of your input plus one query or invocations you have to do it in a classical computer. If you're lucky, okay, you may guess sometimes even before that. You don't have to wait for 9 times. Okay, suppose you have 100 input data, you should do 51. Suppose I have 10, I should do 6. Got it in classical approach. Now at least, can anyone guess how many queries or how many invocations of this function I have to do using quantum computer? One query is sufficient to get the right answer in quantum. So that is the trick. Now you agree? DJ algorithm gave this trick. You just do it once. So how he achieves? He gives the circuit. So this is a DJ algorithm circuit. Normally, we need, depending on the size of your problem, you need so many qubits. Okay, all qubits are in zero state. There are n qubits, though normally this is how you represent. N qubits are in zero state, and one qubit is in one state. So ideally, we would have started from zero, and then we applied NOT gate. You would have got one state. Now we are going to apply Hadamard gates. Since there are n qubits, you need to apply n Hadamard gates. So that is how it is represented like this. And here we have only one qubit, so one Hadamard gate. Afterwards, we have this block box function, okay? And this function is done, written in such a way as I think yesterday you would have seen that any operation, whatever you do, all operations can be represented by a unitary matrix. And because of that, the number of input and the number of outputs will be same. So it is done in such a way that not only it has got f of x, but for x it will give the x, for y it will give y xor f of x. Okay, all right. Then afterwards you just throw it. You only look at it, and then you apply Hadamard gate. Looking at the answer, you can say this is constant or balanced. Magic, right? So let's try to understand a little bit here what happens in this oracle. So when I apply, when it Hadamard gates, what you will get is uniform superposition of all states, right? And when you apply Hadamard gates again, you will get all zeros back. But that is not happening because of phase kickback. This guy does something to the states. That is why you don't get all zeros. If you get all zeros, then it means something. If you don't get, it means something else. That is what we are going to see. So typically we do the analysis like this. What happened mathematically? We try to understand what's happening at each stage of these gates, okay, in the circuit, each stage of these circuits. So we started with zero state of all the n qubits, and one qubit is in one state. Now when you apply Hadamard gate, so we get okay, first we apply Hadamard gate to this, so that will give like this. Very easy, we are familiar. So this one we are getting something little odd. It involves everywhere, all the algorithms. They use thoroughly the mathematics, not complicated, but involves multiple steps. Okay, so that is where we should have patience. All right, just for you to make you understand what does it mean, I'll just say, suppose there are two qubits. I apply Hadamard gate to both, so I'll get plus state and plus state. So I can simplify further by multiplying 0, 0, 0, 1, 1, 0, 1, 1. That's what you say. Instead of representing like this, okay, for 2 qubits, you are able to represent. Suppose I have 1000 qubits. Can I put all those things? We'll go mad. So instead of that, they put it in simple way, where X represent all possible combinations of that many qubits. Okay. All right. So that is what is being done here. For n qubits, it is so the length of this is n. It represents all. So this is a uniform superposition of all n bit strings on the data register. So people call it as register if you have set of qubits. Okay, so don't worry. Or you call it input data, input register or data register, ancilla or target register. It's tensor with ancilla in minus. Okay. Now we applied this. Now we are going to apply the oracle. So according to the definition, it will take x and y and it will give x and y XOR f of x. So let's try to do what happens. Y, we know what is y, right? Y is nothing but 0 minus 1. For time being, don't worry about the normalizing factor. All right. So you represent 0 minus 1. So 0 XOR f of x. So 0 f of x, okay, so it doesn't have any impact, so it will become f of x only. 1 XOR f of x, the output is unknown because it depends on the value of f of x. So let's, f of x can be 0 or 1, right? So if it is 0, what happens? So this will become 0 and this will become 1 XOR 0, which will be 1. And in another case, x is f of x is 1. So you put 1 and this is 1 XOR 1, which is 0. You got this one. So they are same, right? Except that there is another negative thing here. So that negative thing, it gets pushed to this place, face kick back, okay? And this guy will stay very cool. Now that kicked face comes to this uniform states here, all right? Now we are going to apply Hadamard gate. This is little more complicated, but again, nothing very difficult for all of you. So basically, we are going to apply Hadamard gate to already state which are already we have multiple state. We are going to apply Hadamard to multiple states. So it becomes very complex. So in order, how do we represent in simple way? So that is what is being done here. So for example, even take a single qubit, h of 0, we know this is like this, h of 1. For single qubit itself, two equations. Suppose we have n qubits, 100 qubits, become difficult. So I want to represent in a single equation, right? So that is what is done like this. By taking, so b can be 0 or 1 and y is also 0 or 1. So you have now 4 combinations, right? So all those things can be expressed. So because of sum, you will get 0 and 1. Okay, so for every b, you get this one for, okay. I hope it's clear, right? Because this is an important step. So you will be able to represent as a common single equation instead of having so many equations. So that is what is being done here. So for 2 qubits, it's okay. For n possible state, right? So you represent like this. So what is this new variable? So this is nothing but like x only, uniform superposition state only. For if it is for 2 qubits, this also will be 0 0 0 1 1 0. Okay. But the only difference is something gets added here because the sign, now we are worried, I mean, it's getting disturbed, right? So that is represented like this. It's operation called x dot x. It's bitwise dot product modulo 0, meaning both are having same size, right? So you take each bit of it. So you have another 0 0 0 1 1 0 1 1. So you take each one and then add them, divide by 2 the remainder. So ultimately you will get something 0 or 1, okay? But there is a way to get that number. So this is nothing but minus what you saw here earlier case, right? So we applied h of n and we are going to, we got the expression from you make use of this and trying to write. And this remains same. We just neglected this guy because that will add further confusion. Anyway, we are not bothered. Okay, so you got, okay, so this two can be combined. That is what is done, minus n, and further it can be simplified to this. Okay, so when you make a measurement before that, so it looks very complicated, but nothing great. So what happens? I'll give this table so that for a 2-qubit states, we'll have I'll try to put a truth table kind of thing. So X is one of the possible 4 states. Z also is one of the is sum of over all the things, and the exponent X dot is bitwise dot product multiply. So I'm going to consider a balanced function, meaning out of 4 possibilities, for 2 inputs it will give 0, and for 2 inputs it will give 1. So right, this is the f of x, and z I'm considering for 0 because z will take sum of all the things, right? I need to, it will have all 0, 0, 0, 1. So I'm starting with only 0, 0 condition. So I'm putting all zeros. Now x dot z will be 0 because x z is 0. Now f of x plus x0, this simple addition. So you will get same thing like here because this is 0. And now if you apply minus 1, so what happens? Whenever it is 0, it will become plus 1. Whenever it is 1, minus 1. Correct? This is what is represented by this guys. I hope you understand. It's not very complicated, right? So now let's take another case where the f of x is constant, which will give all ones. You can also consider all zeros also, but now let's see only for all ones. Again, we are trying to do this computation for z equal to 0, 0. So when you do this, you'll be surprised to see all 1. If you use 0, you will get all plus 1, right? Whereas here, so this is what called interference. So the state z for being 0, 0, this will get cancelled out. So destructive interference will take place here, and constructive interference will take place here. So this is the power of quantum computing and DJ algorithm utilized. Okay. So at the end of this, if you make a measurement, the probability of getting all zeros, get all zeros equal to 1 if f of x, if f of x is constant. You have seen it, right? So either it will be plus 1 or minus 1, but it will give the maximum rate, possibility. If you get any other number, then it is balanced. So what number you will get when you're making measurement? So you suppose you get all zeros, it is constant. If I get something like this, then it is balanced. And what number? It depends on what f of x you are using. Excellent, right? So the trick is you do once from left to right. Sorry, from left to right. Make a measurement. If you get 0, it is sorry, it's constant. If you get any other number, it's balanced. Very simple. Blindly, a child also can do. So trick number 1 is over. Now let's move to trick number 2. I wanted to show you the maybe at the end, if we have time, we'll see the code. Okay, now source trick we'll see. Source trick is known to most of you. So he gave the trick for finding prime factors of an integer. So he's an American mathematician, and he released his algorithm in 1994. Classically, factoring large numbers takes exponential time. Source algorithm runs in polynomial time. That means you are getting exponential time advantage, right? But he uses, I think we have seen it earlier, a quantum Fourier transform approach. It can be used to RSA cryptography used in online transactions. So that's why, you know, people are talking post quantum algorithms. Okay, post quantum cryptography algorithms, and this is much faster than the most efficient non-classical factoring algorithm. You know, to break RSA 2048, which uses 617 digit number, it takes many years. Okay, but if we have a perfect quantum computer, today we don't have, you can do it in few minutes. Okay, so our online transactions are still safe. All right. So what he studied number theory. Okay, before giving. This is nothing to do with the quantum. This is pure classical number theory. Okay, so in order to factor a number n which has got factors p and q, and the problem will be complex when p and q are odd prime numbers and they are roughly equal, then brute force is going to be impossible. And that's why we are safe, right, with RSA. But still you can do the factoring by guessing some number x. If you are able to guess some number x, which gives x square when you do the division by x square, if you get a remainder 1, then you got the answer. Of course, there is a condition that when n divides x, you should not get the remainder 1. So what does it mean? X square equal to 1. So x square at minus 1 is 0, which means it perfectly divides without a remainder. So what we are saying is n divides x square minus 1, and we can also say x minus 1 into x plus 1. They are factors, but x square minus 1, right? But n doesn't divide x minus 1 or x plus 1 as per this. In that case, if you take GCD of n and x minus 1 or GCD of n and x plus 1, they will give the factors of n. So as in sample thing, if you say n equal to 15 and if you are able to guess 4, then x square equal to 16. 4 square is 16, and when you divide by 15 you get a remainder 1. Okay, means you got it. Okay, x minus 1 plus x plus 1, that is 4 minus 1 by 4 into 15. Now you take GCD, you get the answer. Okay, so the difficulty here is getting x. Again, even with brute force you will take many years. Now Shor came out with a different way of getting that. Instead of getting x, he said, if you guess r, don't guess a. And instead of x square, ideally a square, instead you do this one. Then you will get an answer. That's what he said. Okay, so he proposed a classical check, sanity check. Okay, you get the number to be factored and you guess a, if a should be greater than 1 and then less than n minus 1, and then you take a GCD between a and n. If you have GCD, if you get any GCD greater than 1, that means you got an answer, you got the trivial factor. Okay, I mean you got already a non-trivial factor, you need source algorithm, but generally that is not the case, right? So you come here. Okay, so guessing A is still there and finding R. So he proposed a very, very nice algorithm. He made use of quantum phase estimation algorithm to get this R. Okay, so our whole exercise, the crux of source trick or source algorithm is to get R faster. Okay, arrive at unitary matrix. Okay, QPE steps has got, you need to get a unitary matrix. You generate some circuit with some counting registers, work registers, and then apply controlled unitary matrices from here to here. Then once you do that, what happens is the relative phase so will get kicked, and then you start getting some thing which you convert back to numbers using QFT inverse, and then you make a measurement. Okay, and then that will be, you call it as K, and since we use the number of qubits more, so you have to divide by the maximum possible number, which means that you have to divide K by 2 to the power of m, because, and that will be a fraction always, it will be between 0 to 1. So which represents something like S by R. Now that's all, quantum is done. Now you have to come to classical processing. So there are algorithms, continued fraction algorithm to extract R. Okay. So only thing you have to do, again some sanity check. R should be even because you need to take a to the power of R by 2, and that should not be equal to minus 1. We had similar steps in classical number theory also, right? Okay, so now compute if this condition is met, then you take GCD of a to the power of r by 2 plus minus 1 comma n, then you will get non-trivial factors. But if this check fails, you pick a new a and repeat. Then now you may ask, oh, how many times? It's like there also we guessed x, here also you have to guess. But source also has given how many times you need to guess. The probability of guessing the right a is given by this expression, where k is the number of distinct odd prime factors. Okay, so in this case 2, so it is 1 minus 1 by 2 square minus 1 to the power of 2 minus 1. So this is nothing but zero point 0.5, which means even if you guess two numbers, there's a probability of getting the right one is there. Okay, and so you don't have to really guess too many A's. Okay, so now how to do QPE? That's what. And why is it called period R? He called it as period R. It's because, okay, first of all, what is it? The period of R is the smallest non-integer. Okay, there's a definition, sorry. Non-integer such that x to the power of R mod n equals. So this is the fundamental thing, right? So why it's called period? We'll see an example. Suppose n equal to 15, x equal to 2. So you do 2 to the power of 1 mod 5, which is 2. 2 to the power of 2 mod 5, which is 4. But when you come to 2 to the power of 4, mod 15 is 1, right? Because 2 to the power of 4 is 16. 16 by 15 will give a remainder of 1. Again, you move further on 2 to the power of 5, you will be surprised to see that is 2, 4, 8, and 1. So you can see every fourth parameter you will get. It repeats after every fourth. So that's why it's called period. And any periodicity, this guy will immediately catch with some his own magic way. And that is done with the help of this expression. This, okay. So if I take a unitary matrix, and if I multiply one of its eigenstate, I will get value times eigenstate, and I'll be able to get this value, and from here I will get this one, and this will give me R. Okay, that is what is the Q of t, advantage of Q of t. Okay, so what? Sorry, QPE, advantage of QPE. So how does it look like? QPU circuit. This is a standard circuit. It's not source circuit. Okay, quantum phase estimation algorithm is, it's also called quantum eigenvalue estimation algorithm. Is a quantum algorithm to estimate the phase of an eigenvector of a unitary operator like this. I think you are familiar, I hope, that even in linear algebra, when there is a matrix A is acting on its one of the eigenvectors, what you will get is the corresponding eigenvalue lambda into this. Same thing is applicable here in quantum computing also. That is what we are going to do, and this guy will be able to generate from here, and from there you will get R. Okay, let's see the circuit. Let's try to understand the circuit. So it has got two sets of qubits. The first one we call as register. Okay, phase or counting or T or M. Okay, so depending, I mean, different people use a different one. You can, so I taken this picture from the Bible. Okay, later you'll see the textbook. They call it as T. So how many qubits you should have? You should have 2 times log n. Okay, suppose the number to be, it's a huge number of qubits. Determines accuracy and probability of success. Okay, so then only you get better accuracy and better probability of getting the right R. Okay, the work register, this is called work register. So you just it will work and die off. We don't bother. Okay, so it's, and how many qubits you need? Half of this, just log n qubits, right? Here twice log n, here just log n. Okay, some people call this as yum y and all. Okay, so don't worry, but you should be clear. Okay, so this is called work register, this is counting register. U can be arrived at different ways. So today we are going to see a method called permutation matrix. This is good for smaller size n when you are working, but for a large n, this will not scale up. For that, you have to literally write the circuit in a different way. Okay, and using quantum gates only, right? So that, of course, there's a lot of research going on how to get U. Okay. Ideally, the work register should represent all eigenstates of U. So that is the condition, right? So we are saying that this should be the eigenvector. Again, so that is the trick Peter Shor said was the state 1 is used because he used just state 1 because it's an equal superposition of all eigenstates, okay? And in this circuit, I didn't show that normalizing factor 1 by square root of n blah 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 blah. Blah. And then you also need to do QFT inverse here. Why should you do QFT here inverse? It's because all this will become Fourier basis, meaning it will be you get the angle, the phase angle effect will be here, but you need to convert them back to measurement basis, that is in terms of 0 or 1. So that is what is being done by QFT inverse. Okay. I'm not going into the detail because there is ready-made function available in IBM QuizKit. You just call, you say how many qubits are there, it will do the operation. In fact, the source algorithm itself was given earlier in the initial days. You say source bracket 21, you give it will return 7 and 3, but they removed for some reason actually. All right, so arriving at U using permutation matrix. So what is permutation matrix? That will look like this. So what is the specialty of this? So if you take any row or any column, there will be one element which will be 1, all other element will be 0. And what order we are going to put, so that is what is determined by this equation. So you start with any y, 0, 1, 2. And for every y, you calculate y dash. So what is y dash? Which is a to the power y mod n. Okay. If y is less than n. If it is greater than or equal to n, you put y. So this is simple. You get y dash for every y. And then use that for every element having u y dash and y, where there is a match, you put as 1 and all other entries are 0. So what is n? The n is the number to be prime factored. What is a? A is any guess integer, it can be anything. Only condition is that it should not have a common factor with n, non-trivial factors. And power is nothing but 2 to the power of j, and j can vary actually because you may have to do multiple times. Okay, all right. So now let's start with j0 and we are going to do the compute. So y is 0, 1, 2, 3 and 2y mod 3. I'm trying to do 2 times y because a equal to 2, right? A to the power of 2. A power is 1, but so you get a. So this is here. For power 2 to the power of 0, you get a as 2 only. So 2y mod 3. 2 into 0, 0. So y dash is 0. 2 into 1, 2. Mod 3 is 2. 2 into 2, 4. Mod 3 is 1. 3 is written as it is. Now you got y dash for every y value. So using this, so those elements y00, y21, y12, whatever you are taking here, that should be having 1 and remaining elements are all 0. Though the values in the matrix are just zeros and ones, I mean initially we get doubt, but the pattern is unique for each pair of y dash. So literally we have done the mathematics here. Okay, got it. But you have to do it manually, one thing. And second thing, okay, this is simple. You will be able to get this number, store it accordingly. But if when you are working with very large number, it's impossible. Okay, so you have to build that U itself with multiple gates. Okay, so that's called modular. This is again this is one of the methods. In fact, you guys can work once you become a specialist, you can come out with your own ways of doing it, or even you can outright remove the QP itself, can come out with some other methods. But QP is certainly giving the benefit of speed. Okay, so it has got multiple operations. Okay, so the power is converted into addition. Okay, like 2 to the power, suppose I have 2 to the power of 8, I will do try to do it in simpler way and then try to add, and then multiplication I do like repeated addition, even mod operation they try to do some subtraction. So it's there's a lot of mathematics involved in it. It's all possible, you can get to many references, I'm not going into the detail, but these steps will remain same like whatever you saw for permutation matrix. Okay, so once after QFT, you make a measurement and then divide by 2 power n, you get some number, right? Some real number. Okay, from there you can get using continued fraction algorithm. So which means if given any number, you can represent by 1 by some numbers, and then you can keep going like this till you get the required accuracy. And you don't have to break your head, but first of all, this is not a quantum algorithm. This is very purely classical algorithm. And more than that, there is a fraction class already available in Python. You have to just call that. Okay, so you give your face value or s by or here value, it will give directly. Of course, you have to do limit the denominator, r cannot be more than n, right? So that is what is being done. So afterwards you will check and then you compute, you get the numbers. So now you have understood source magic, right? So these are all the steps. If you have any doubt, maybe 1 or 2 questions we can take. Otherwise, I'll move on to Grover's magic. So we are going to see the hands-on at the end. So what is Grover's magic? It's an algorithm proposed by Love Grover, an Indian American computer science scientist. He solved the problem of unstructured search at a efficient way. Okay, so it's also possible to do in classical way, but he did it faster than that. It's a quantum algorithm for finding an input. So the definition is like this: I have set of x values, many, okay, out of which only one I'm interested. So I need to, so I have a function which will return one for that particular x, and for all the remaining x's, it will give 0. Okay, that is what it is going to do the search operation. That's how, right? I'm interested in a particular data in the database. A typical example can be considered like this. I hope you all know what a telephone directory, right? So if you are working in a company, you will have a telephone directory. Earlier, when BSNL was very popular, we used to get telephone directories. In fact, the last they released was 3 volumes. It's a very big, each one weighing more than 2 kg. So you will see, but it's still easy to get the phone number of any person because it's nicely sorted alphabetically. So you look for the name, you will get his number. It's a very good thing actually. Assuming that instead of giving it in alphabetical order, it was unsorted. Okay, so it's going to be tough thing, right? So how many times you need to, how many names you have to look for? If you're lucky, the first name itself will be the name of your interest. But if your luck is very bad, that may be at the last one. So on an average, you need to do n by 2. I'm sorry, on n by 2 queries or n by 2 search you have to do. With Grover's algorithm, you can do it within square root of n. So you get a quadratic speed up here, but people are not happy with quadratic. In fact, they want to see how can we get faster than that. But this itself is a great thing, right? Suppose I have 10 lakhs data. I may do it on an average 5 lakhs. But if I have Grover's algorithm, I can do it in 1,000 steps itself, correct? So people are trying to extend this for cryptanalysis to search the key, because basically it's like a brute force method, but brute force also can be done faster, right? Because that's all you do optimization. You want one number, right? Similarly, in cryptanalysis, you need one key. So what is that key which does something, right? So that is what you can use it as a search problem. Similarly, in drug discovery, all right. So what are the steps involved? So first, you represent all the states. Okay, how? By applying Hadamard gate. So depending on the size of your problem, you represent everything, and we are familiar with this, right? Sorry, we are familiar with this one, and we call them as state S, which basically represents superposition of all possible states. Now we need to define unitary matrix U, okay, as a block box. You can do it, which will mark as -1 if f of x is 0. When f of x will be 1? When x is equal to omega, which I'm interested in. Okay, that's what I'm searching. For all other things, it doesn't do it, just leaves it as it is. If f of x is 0, that is, x is not equal to the what our number or whatever name I'm looking for. Okay, so by with this, can you get the answer? No, you won't get the answer, because when you make a measurement, still you will get all other numbers also, because their amplitude is same. It's only negative, right? But the probability is still the same, because probability is nothing but amplitude square, right? So whether it doesn't matter whether it is minus or no. So the only thing is how to increase this value up for this input alone. For remaining, we need to bring down. That is what is done by something called diffusion operator. He invented that. He called, so basically what it does is, for the given state average, it will make some reflection. Okay, that's magic. So this is what is the trick what he did. It reflects amplitudes through uniform status. Okay, you will understand better in the subsequent slides. And this he gave it as an expression here. So this is a very well known expression, 2 into outer product of S. What is S? S is nothing but a state representing all states, superposition of all states minus identity matrix. And you need to repeat these two steps, G, okay, D and U. How many times? K times. So what is K? K is given by this one, root of N. Okay. Generally, you don't have to go that far. Even well before that, you will be happy to get that required one. And sometimes people don't represent this number, but this is the mathematical way. And you have to apply this marking also repeatedly. Okay. Why? Because each diffusion step redistributes the amplitudes. Okay, so you need a fresh phase flip every time. All right, you may say, well, first time I've done. So this is just for your information. Okay, so now this is easy to do. First, let's look at that. So basically, you make a comparison, right? For example, I want to, so my oracle will do this job. Okay, -1, and whenever f of x is 1, that particular x will be flipped. So if I want to flip this guy, what I can do is I put one more x here for this qubit, and then it will become 1, and I can use any controlled x gate, right? So that will flip it, and then I'll do undo my all operations. So my state of 0, 1, 1 will be marked by this circuit. Okay, so this is with an Angela bit. Sometimes I will not have sufficient qubits, pair qubits, so at that time I'll go without Angela bit. Similar exercise I do, instead of controlled X gate Z and control X, I'm using control Z gate. Okay. Now here it is identified differently, control target. Here There's no difference because control Z gate, whether irrespective of whatever, whichever may be the control or target, the effect will be same. So that is why they write like this. So when to use what? It depends on the hardware what you are working. So don't worry about that. Both will work if your hardware accepts. Okay. So we started with yes, and we built an oracle which is marking. How that happens is by knowing what you are looking for, and y minus 2 like this you do, you will get a state which will have marking on it. You can also represent like this. Okay, you have all possibilities except x star. X star is having a different amplitude. Okay, now the oracle is built, that is marking is done. Now I have to do diffusion, right? So how do I do that? So for that, Grover gave, okay, this you got already uniform by applying Hadamard gate. That one you do in outer product, you do it, okay, and then multiply by 2 and minus identity matrix, you will get the inversion about average. Okay, so this does inversion about average. So how this will help later, we'll see it in graphical form. All right, let's take an example. So I have all uniform states, right? Which is for a 2-qubit system, it is 0, 0, 0, 1, 1, 0, 1, 1. So typically we represent like this. If that is all uniform means 1 by all are there. 1, 1 amplitude is 1, 1. So that is what is written here. Okay. So since for want of space, I put in row form, but I put a T transform. So now taking outer product. So I will get a square matrix because, okay. So it will become 1 by 4 into all ones. And we know identity matrix, right? Where the diagonal elements will be 1 and all other elements will be 0. Now I multiply this matrix by 2 and then subtract it from I will get this matrix. This is nothing but my D matrix. Okay. Now if I am interested on this vector, or I mean just you take any vector in fact. So what it does is inversion about average we told. So what is average? Average value of each vector is 0.5. Now if I apply onto this, you will get another vector like this, wherein the average it will have an inversion, for example 0.5, 0.5, because there is no it is right sitting right on the average line, whereas 0.2 will become 0.8. Why? The difference of 0.5, sorry, 0.3 will get added and you will get 0.8. Similarly, the values which are above 0.5, they will become less because that is how the inversion, right? This is 0.5 means somewhere if it is here, it will be here. But if it is here, it will be here. Okay, so that is what the reflection. So very nice mathematics. This is purely classical. Now, how do I implement in quantum? So that is where Grover's trick. He gave that trick. Okay, before that, I want you to understand. So what the steps involved are: you apply a set of Hadamard gates to all your qubits, then apply a set of H gate, then use control Z gates linking all the qubits. Then again you undo the operation. Whatever you are doing here, you are undoing it. When you do that, okay, there is some mathematics, you can understand what happens at each stage. So typically you apply at that time what happens. So I'll not go into the detail, but this table will give you some idea. So we started with all possible states having equal amplitude, right, initially. Then after applying oracle, which I am interested in 0, 1, so this phase alone will get flipped. Now after applying Hadamard gate, you can verify it. Okay, what happens? Sorry, this move to this place, this sign. Now when you apply X gate, the states are swapped interestingly. So they'll go like this. Now I'm applying Z is Z gate. So what it does when all are for all one case, it will add a phase. That is what it's doing. Now I'm going to undo my calculation, which basically again it will swap. So whatever I applied minus, it has gone there. Now after applying H, you'll be surprised that all are gone. So only one, the one what we are interested. So this is again interference. Okay. So the right one got constructive interference and the wrong ones got destructive interference. Since we are working on 2 qubits in one iteration itself, you got it. Otherwise, you have to do square root of n iterations. Okay. All right. So mathematically, this also can be expressed in a way. Okay. Suppose initially we have all uniform states, but I'm interested only in this. I want to flap that. So first I'll do this negative sign. Okay. Now the average will be coming down because this guy has become negative. So how much it comes down depends on how many entries, what are their values and all, right? So, but fundamentally it will come down by some margin, by some level. So now this is the average. I want to make a reflection about with respect to this axis. At that time, what happens? So you will, this fellow will go like this all, and this guy will go little more, right? Because it's far off. So this will go like this. Okay. Again, how much? It depends on the problem. And then if you are happy, because slowly what we are trying to say is the amplitude will keep rising it. You do multiple take average, flip it, and then keep doing it. Okay. Slowly, the amplitude of this guy will keep increasing, and all others will keep down. Some point of time, if you are happy, you go with the value. It can also be represented in other way in matrix in vector form. Okay, this is graphical form. This is in vector form. So this is what I'm interested. Okay, and this is what I have on my hand. This is nothing but this one without that. Okay, and they will be perpendicular. They are all orthonormal basis. Okay, I'm using some term. Okay, don't worry about that. Rotating s with respect to s dot. So I'm going to rotate this. So what is theta? Theta again depends on, in fact, square root of n. Okay, so theta depends on the omega value and the s vector. So we'll not go into the mathematics now. So it gets reflected. Okay. So from here it has come now. Now taking this as reference, if I do another rotation, I'll get like this. At that time, this will become 2 theta. So like that, I'll keep doing. Slowly, my answer, the final vector will approach this guy. All other states will lose its amplitude. Okay, so that is what is done here. Okay, so this is how many times you do the reflection. So don't worry, they are all not scaled properly because theta will be in general will be a very small number. Okay, the probability of getting the right answer to one is so many reasons. All right, now let's get into the hands-on, which is will be very useful for you to understand as a code. All right, so let me go back. So we'll see all the three tricks. Okay, I'll start with DJ algorithm. So I'm trying to build an oracle for constant, oracle for balanced. Instead of writing two programs, I'm trying to combine in a single program so that we'll quickly get that. Now I need to build the Deutsch-Jozsa circuit, and you know how to build, right? You need set of qubits representing all possible states depending on the size of the problem. Then you have ancilla qubit. This is called data qubits. And then this is the oracle built for. So I'm drawing the circuit only for balanced one. Though I built both circuits, I'm drawing it here for only one circuit. Then at the end we have to apply Hadamard gates, and finally you have to make a measurement. This you are familiar. So if you run this code, you get that. Okay, this circuit has come now in, but while running, I'm running to both the things separately, and but for plotting, I'm putting the answers together. You can see here, I'm running twice and then converting into bits because it will come normally zero. Okay, okay, 0, 1, 2, 3 like that. So when we plot, you can see here for a constant function, you get full probability on 0, 0, 0, 0. For balanced one, you get any non-zero. Okay, can be anything. It can be 1, 0, 1 or all ones. It depends on what function you are using, what function you have used here. Okay, now you can check. So 3 means 8 combinations are possible, right? 8 possible inputs. So which 4 I got will give 0 and which 4 will get 1, you can find out. There are very, very simple things and very interesting. Only thing, it takes some time for you to do that. Okay, so that's about DG algorithm. Now we'll go to source algorithm. So here we have to build the unity matrix. That is what I'm by permutation matrix I'm building. Then QPU circuit I'm drawing. As I told you, we don't have to break QFT because okay, we can simply call the function. It's readily available. Okay, QFT is available in the circuit as a library, so you don't have to break your head. Then we need to extract period by classical computing, right? Fractional class. Okay, I told you. So that will give directly the period. We need to do some sanity check on the R value, whether it's some. Okay, correct. Okay, now all the functions are written, the methods. Now you just putting everything together, we will be able to run. So I'm going to run, of course, factor 21. This is written in such a way. You can modify it for some other numbers, okay, but that's the challenge. Let's run it. It takes long time. Because it has to do multiple operations, right? Many number of times the U matrix will be operated, right? U2 to the U to the power of 2 to the power of 0, U to the power of 2 to the power of 1 like that. Okay, so many number of times the thing is added. Oh, we got the answer, right? So this is how. But again, as I told you, this is not scalable approach. You need to have different approach for getting U matrix. So that's about source trick. Now finally we'll come to Grover's trick. So what Grover's trick, we want to mark say 0, 1. So this oracle is built for that. And this is the circuit, and you know that circuit, you have to bring uniform states, sorry, superposition of all states. So by having a Hadamard gate, then this is the one which helps us to mark 0, 1. You can check as a circuit what happens. Okay. Then this is diffusion operator where you know H, X, of course, control Z only I told, but here I'm showing H control, which will have a similar effect. Then you have another set of X and another set of H. Afterwards, you make a measurement. I'm making the measurement here. Then run it. You get, oh, let me run it again. I'm sorry. Okay, something. I didn't run this step. I was just quickly running this, so I didn't get the right answer. Okay. But two is 1 0. That's wrong because actually the convention of IBM Qiskit is different compared to the way we write binary number. Okay, so that's why you got to, but actually the answer is right. Only the way we interpret is wrong. Okay, to avoid the confusion, we'll take some other number. We'll take 3 big qubit system wherein we mark 101, so the order doesn't matter, right? So let me mark 101 here. And also we'll learn one more thing. So same thing, we need to build the oracle diffusion operator. Then we'll run it. Let us see how it runs. Oh, got the answer 101. Uh, oh, sorry, I'm running it here. So it gave the answer. Okay, with this one alone, higher probabilities with one iteration, but this is not sufficient. Okay, so this should be much more. Ideally, you should get uh, one probability. So for that, we are repeating the circuit here. You can see here, first iteration, second iteration, same thing. It's just repeated here. Now you will see the amplitude or the probability increased from 0.781 to 0.914. If you do it again, okay, ideally this is 3 qubit system, which means 8 inputs are possible, right? 8 points. So you have to root square root of 8 is 2.8, right? So even with one itself, you are able to, this is what I was telling you earlier. You don't have to really do so many square root of n times. All right. So that's the end of my presentation. These are all references. So I request, so online IBM documents are too good. In fact, I'm sure even Microsoft or Google documents are good. So whichever you are comfortable, you can follow. And there are plenty of YouTube videos coming from IBM QuizKit and from me. So please go through. I have almost on every topic. Whenever you get time, please go through that. And I think there are different series of QuizKit lectures. Go through that. That's all. Thanks for your patient listening, and then we'll have some question and answer.